good morning to everybody. I'm very pleased and honored to be here this morning at the Engineering Education for a Sustainable Future online conference and to talk with you on navigating sustainability through energy efficiency and renewables. Dear colleagues, members of the global energy community, climate change nowadays, energy security, geopolitical crisis represent shared concerns for governments, policymakers, responsible investors, and the scientific community. And for this purpose, several initiatives and proposals and packages have been introduced in the last few years to mitigate global warming, to reduce the dependence on fossil fuels, and to tackle the continuous fluctuations of energy prices. At the European level, among the others, the European Green Deal aims to transform Europe into the first climate neutral continent by 2050. With a decrease in the net greenhouse gas emissions higher than 55% by 2030 compared to the 1990 values. And all the United Nations member states adopted the very well-known 2030 Agenda for Sustainable Development in 2015 to provide a shared plan for peace and prosperity for people and the planet. As you know, and as already introduced, the 2030 Agenda consists of 17 sustainable development goals that represent a crucial call for action by all developed and developing countries in a global cooperation in order to protect the planet, contrast poverty, and improve lives and prospect for everyone, everywhere. In particular, a specific and dedicated goal, the number 7 of the agenda, concerns energy, with the aim to ensure affordable, reliable, sustainable, and modern energy for all, increasing significantly the share of renewable energy in the global energy mix, and doubling the global rate of improvement in energy efficiency. And reaching the sustainable goal on energy will promote actions to combat climate change and achieve many other goals, including better health, for example, number 3, more sustainable cities and communities, clean water and sanitation, more responsible production and consumption, innovation, number 9, sustainable transport, food security, poverty eradication, also economic growth, and quality education. And a global roadmap has been defined to be sure that collective efforts meet energy target and net zero emissions of the Paris Agreement. For this purpose, by 2030, it is necessary to triple renewable power capacity, double the global rate of improvement in energy efficiency, triple annual investment for renewable energy and energy efficiency globally, phase out coal power plants within the OECD community, create 6 million jobs in renewable energy and energy efficiency, and guarantee universal access to electricity and clean cooking solution. However, the deployment and the exploitation of renewable energy is lagging, especially in transport sector, heating and cooling applications. Furthermore, the global energy efficiency improvements must increase significantly, and the phase out of coal power generation needs to be accelerated globally. To this end, cooperation between all stakeholders, including countries, international organizations, development banks, civil society, scientific community, universities, cities, government should cooperate in order to define a clear direction and enable proper conditions for energy innovations and technology development. At the same time, more investment in renewable and energy efficiency worldwide is required. In this context, shifting for fossil fuels subsidies to renewables and putting a price on carbon represent fundamental factors to speed up the energy transition. And furthermore, international cooperation has to be enhanced to promote technology transfer towards developing countries and to attract public and private finance and investment. The energy transition and the possibility to meet global energy targets and mitigate climate change risks are based on two main pillars: renewable share increase and efficiency improvement. Increasing the share of renewable sources, in fact, means reducing the greenhouse gas emissions and pollution, providing a green alternative to fossil fuel import, reducing the dependence on external suppliers of traditional fuels, lowering energy bills, supporting a sustainable growth of the economy, and improving the quality of life. And the deployment and exploitation of renewable sources is shown in this slide, and it influences directly the global access to affordable, reliable, and sustainable energy. However, the share of renewable energy in the total final energy consumption remains low at global level, despite the increase that is visible in the slide in renewable energy consumption, the bars in the figure. The current trend is not in line with the international targets and climate objectives, and the penetration of renewable energy must be accelerated. In fact, in 2022, the global share was about 18%, not much more than the 60% that we registered 10 years ago. In this context, the global contribution of renewable sources in final consumption is greatest for electric generation and corresponds to about 30% for electricity, while heat represents the largest energy in the use worldwide, accounting for half of global final energy consumption. But the sector remains heavily dependent on fossil fuels that satisfy about 80% of the global thermal demand, while renewable sources reach about 21%, and traditional uses of biomass correspond to more than half of this percentage. The transport sector is the end-use sector with the lowest renewable energy penetration, corresponding to only 4% of final energy consumption in 2022. And in this context, liquid biofuels provide 90% of renewable energy consumed for transport, with most of the remainder coming from renewable electricity for vehicles and trains. At this point, it is interesting to notice that the increasing competitiveness for renewable power, especially for electric productions, continues to provide the most compelling pathway to decarbonization of the global energy system. And according to IRENA report, the table compares the total installed costs, the capacity factors, and the levelized cost of electricity for different renewable technologies on the left-hand side in 2010 and 2024. This is for electric generation. And a significant decrease in the levelized cost of electricity has been observed for photovoltaic, concentrated solar power system, and onshore and offshore wind systems, with a decrease in levelized cost of electricity ranging between 60 and 90%. And this other slide shows the trend in the last 2 years, 23, 24, for all the renewables technologies. And this other slide, always from IRENA, confirms that the 2022 fossil fuel price crisis has shown the economic and security advantages of renewable power generation. And the last years have registered, in this case, among the highest rises in the competitiveness of renewables, as visible in this slide. Just as an example, in 2010, if we consider, for example, onshore, the levelized cost of electricity was about 126 higher than the corresponding lowest value of fossil fuel-fired power plant production, while in 2023, the worldwide levelized cost of a new onshore wind project was about 60% lower than the cheapest fossil fuel. This is the fossil fuel cost range in the period that we are considering between 2010 to 2023. And it is interesting to notice this significant decrease in terms of cost. And similar results are visible for photovoltaic system that have reached higher improvement. We move from about costs that were about 400 more expensive. This is the value corresponding to the minimum values of a fossil-fired solution. And now they are about 56% cheaper than the lowest fossil fuel system in 2023. And the results highlights also that renewable sources reduce the economic cost of exposure to volatile fossil fuel prices, reducing the need for traditional fossil sources and their import. For 2023, the renewable power deployed globally since 2000 saved about 500 billion of US dollar in terms of cost, fuel cost in the electricity sector, with the main share from Asia with about 200 billion and Europe with about 90 billion. And the main energy come from onshore wind and hydropower. As already introduced, the second pillar to promote a proper and effective energy transition and to guarantee a sustainable and green future is based on increase in the energy efficiency. Energy efficiency, in fact, reduces overall energy consumption and is then crucial to achieving the climate ambition, enhancing present and future energy security and affordability. Saving energy represents the most cost-effective solution for a more climate-friendly energy system. In fact, using less energy has direct benefits for the environment and guarantees lower greenhouse gas emissions and pollution, reduce dependence on imported fossil fuels, and provide more affordable energy for citizens. And particularly, energy efficiency needs to be improved, considering the complete energy supply chain from production to final consumption. For this reason, at a European level, a new energy directive has been approved in September 2023 to ensure that the EU target of decreasing greenhouse gas emission by at least 55% compared to 1990 values can be satisfied together with the other energy and climate rules. And the revised directives defines energy efficiency first as a central principle of a European energy policy. In practical terms, this means that energy efficiency must be considered by EU countries in all relevant measuring policy and major investment decisions taken both in the energy and non-energy sectors. Furthermore, the EU targets are significantly raised, making it binding for all European Union countries to jointly reach an additional 11.7% decrease in energy consumption by 2030, compared to the 2020 reference scenario projection. And the Sustainable Development Goal number 7 target aims to doubling, as already said, the global rate of improvement in energy intensity over the average of the previous 2 decades. And this corresponds rising the energy intensity by 2.6% per year in this period, with respect to the period between 2010 and 2030. I remember that energy intensity is the ratio of the total energy supply to the annual gross domestic product. In other words, it represents the energy used per unit of economic output. And the slide here shows the primary indicators related to our goals for 2025, according to the International Energy Agency report in 2025. The results highlight a significant acceleration in the deployment of renewable energy, while slight gains are in energy efficiency. However, progress towards the 2030 objective is still lagging. And in this context, the role of a university is fundamental. University and education are powerful actors in the sustainability transition. University, in fact, can develop new ideas, high efficiency technologies, for example, solar cells, batteries, and materials. Provide open data for research and innovation, explore policy models, and stimulate critical thinking. But the most important contribution of a university to sustainability is preparing people, as already introduced during this morning. People that represent the scientists, entrepreneurs, policymakers, and citizens who will lead this transition in the future. Within this framework, it's crucial to notice that sustainability and energy are not just an engineering problem. They are also economic, social, political, cultural, and environmental problems. And the university are uniquely positioned to connect these dimensions with the multidisciplinary approach, as said before. And as a reference, I provide my experience and just some brief information about my courses in energy management at the master degree at the University of Calabria in Italy. The course aims at providing the basic knowledge for the management of energy, combining technical skills with environmental, legal, and economic aspects. We analyze traditional and innovative energy systems, and special attention is focused on energy efficiency, polygeneration systems, and renewable sources. Methods and tools for techno-economic analysis and performance characterization are developed during the course in order to guarantee efficient energy management and the definition of proper solutions to meet environmental, economic, and energy purposes. During the course, the students have to perform an energy analysis and an energy management of real cases, considering economic and environmental aspects too. And this slide, in this case, refers to some case studies considering the last few years for some companies in the food sector in Italy and abroad. The main idea is to perform an energy audit, characterize the status quo, and then suggest potential actions to improve the global system efficiency. For this purpose, students are organized in teams of 2-3 people, and they usually propose very interesting solutions to improve the energy, economic, and environmental performance of the investigating companies and promote sustainability. In fact, managers often take the students' proposal into considerations and sometimes have offered them also positions in the companies. Another application for our students concerns polygeneration. Polygeneration provides the simultaneous generation of different energy outcomes, for example, electricity, heating, cooling, steam, hydrogen, chemicals, in a single integrated process. It represents a remarkable alternative to separate traditional energy production, able to assure a noticeable increase in global energy efficiency and primary saving, especially if combined with renewables. But despite their high potential, polygeneration systems are not fully grounded in the energy, providing about only 10% of the global power generation. And to achieve the high expected potential of polygeneration systems, the definition of the proper configuration and operation of the system is mandatory. This means that appropriate energy devices with the corresponding capacities should be selected, also considering the rational operating strategies in the system operation. And for this purpose, in my course, I typically propose my students with the recent study concerning the optimal design, synthesis, and operation of combined cooling, heating, power systems. The case study is used as a reference to evaluate the potential of a polygeneration and renewable sources integration to improve the global energy efficiency, economic viability, environmental performance in real applications. And the students should propose new alternatives, solutions to improve the global sustainability. In particular, this investigation focuses on small-scale applications that present a lower spread than medium and large-scale solutions due to the current technical, economic, and legal constraints and require more attention. For the case study that I will present and I use usually for the students, the annual loads for electricity, heat, and cooling are defined. The annual electric request of a domestic user is about 160 megawatt-hour and depends mainly on lighting systems, appliances, and electric vehicles request. whereas the yearly thermal load is for specific space heating and hot water production and corresponds to more than 1,800 megawatt-hour. Conversely, the cooling request refers to the sole summer months and corresponds to about 200 megawatt-hour. The application, the case study, refers to Italy. And the slide shows the hourly profiles for typical days in terms of electric, thermal, and cooling demand. In this case, the proposed polygeneration system consists of different units, photovoltaic modules, and gas-fired cogeneration units to satisfy the electric demand of end users, while auxiliary boilers is used to integrate the thermal production when the CHP, the cogeneration unit, is not sufficient. Electric and absorption chillers are adapted to meet the cooling demand, and thermal storage units for cold and hot power are used to improve a global performance of the CCHP system. In this way, at least 2 energy supply units for each energy vector are present in the proposed superstructure. Furthermore, the polygeneration system is able to exploit the solar source with the photovoltaic panel, exchange electricity with the power grid, and avoid thermal dumping. And just as a reference, here the table summarizes the production units selected for the investigation. And to define the optimal design operation of the integrated system, a numerical model is developed, integrating 2 conflicting criteria related to minimization of the costs and the greenhouse gas emissions on a life cycle basis. And for this purpose, a bi-objective structure is used. In this way, we consider greenhouse gas emissions for the production, maintenance, recycle, waste disposal of the different polygeneration subsystem, as well as for all the apparatus operation and primary energy sources consumption. At the same time, the total cost take into account the capital investment, the operation and maintenance, and the price of the energy vectors, also considering their time variation. And depending on the relative importance of the cost and environmental criteria, the model provides useful insight on the technologies and capacity to be installed, and defines the proper operating strategies capable of satisfying the energy request for specific application. As an example, when the wave factor or lambda, this is the objective function that takes into account cost and greenhouse gas emission. When the lambda factor is 0, the environmental target has priority, while when the lambda is equal to 0, the environmental target is fundamental. Intermediate values reflect different importance given to the 2 economic environmental targets. And the results are summarized in the plot as a function of lambda values in terms of annual greenhouse gas emissions and annual cost evaluated on a life cycle basis. And the figure highlights the optimal configuration, the corresponding Pareto frontier, the line in green, the ideal point, the circle in blue, and the reference scenario, the red square. And the reference case, that is the circle in red, refers to separate energy production. This means that the sole electric grid satisfies the electric demand of users, while gas boilers and electric chillers fulfill the heating and cooling requests respectively. All the optimized polygeneration systems, as visible on the plot, guarantee on a life cycle basis an improvement both in the economic and environmental performance compared to the conventional separate energy production. The total cost decrease is always higher than 11% and reaches about 20% when the economic objective is a privilege, whereas the equivalent CO2 emission saving achieve 13%. And the multi-purpose optimization suggests installing the maximum photovoltaic peak power owing to the clean and cost-effective exploitation of the solar source. The capacity of the other components are shown in the table when the lambda is equal to 0.5. And the lower operating cost of the optimized polygeneration systems balance the higher investment compared to the traditional configuration. And just the figure illustrated the payback time and the saving emissions for all the optimal configuration. Just brief information, payback period in this case ranges between 3.8 years and 8.1 years, while the combined system provide noticeable environmental benefits that overcome 1,200 tons of CO2 when the emission purpose is a privilege. The optimal design, synthesis, and operation of polygeneration systems assure interesting improvement in the energy, economic, and environmental performance of a combined energy system compared to the separate energy production. And the integration of different technology and exploitation of renewable sources can drive an efficient transition to sustainable and clean energy solution. To this purpose, a comprehensive and multidisciplinary approach based on LCA technique is fundamental to properly account for all the life phases of integrated energy system, from the construction and installation to the operation and final disposal. At this point, I conclude, remembering that the efficient exploitation of renewable sources and the development of innovative and efficient energy system represent the cornerstones to promote a faster and softer transition away from fossil fuels and traditional technologies, and that the role of universities and engineering education is crucial to guarantee a cleaner and more sustainable future. That's all, and thank you for your kind attention.